Welcome back. Today we're diving headfirst into data. Raw numbers, categories, attributes. So we're not just looking at data though. We're figuring out the fastest, the most accurate way to turn all that stuff, dense spreadsheets into insights you can grasp immediately. So for you listening, our mission today is pretty straightforward. We're laying down the basic rules for organizing and visualizing data. We need to know which tool fits which job. Are we dealing with categories or numbers? The goal is maximum clarity, and this is really important, learning how to spot or maybe avoid creating those graphics that are sort of cleverly designed to mislead.
Yeah, that last bit is crucial, isn't it? Visualization isn't just about aesthetics, making things look nice. It's really about guiding perception. And if you choose the wrong chart or even just organize your raw data badly, you can easily obscure the truth. So we need to synthesize the rules for both qualitative, categories and quantitative, the numbers. So the picture tells an instant, accurate story.
Okay, let's start with the categories then. Qualitative data. Let's say we ask a simple question, like, what's your favorite fast food place? That gives us names, groups, right? Attributes. We immediately need a way to organize those answers.
Exactly. And the first concept is really simple: distribution. It just means, what values or categories show up in the data and how often does each one appear. So we'd build a basic frequency distribution. That's just a list, really. Restaurant names and the number of votes each got. But raw counts, they aren't always the full picture. Often what's more powerful is the relative frequency. That's the proportion or the percentage. So if you ask 50 people, knowing 10 picked restaurant A, a frequency of 10, that's okay. But knowing 20% chose it, at the relative frequency, 0.20. That's much more useful.
Right, because that percentage lets you compare it easily, even if another survey asks, say, 500 people.
Precisely. It standardizes things.
Okay, so we have our frequencies, our percentages. What are the go-to visuals for this kind of data? I'm thinking bar graphs, pie charts.
Those are the two classics, yes. A bar graph seems really straightforward. Categories on one axis, frequency or relative frequency on the other. You draw rectangles for each category. But there's a key rule.
Wait. Is it about the width of the bars?
Exactly. The rectangles must have equal width.
Why is that so important?
Because if you start messing with the widths, making some bars wider than others, you visually distort the comparison. A tall, wide bar looks way more significant than a tall, narrow one, even if the height difference isn't that large. It's a classic way to, mislead.
Okay, equal width. Got it.
And even with these basic charts, there are refinements that make them more powerful. Think about the Pareto chart. It's still a bar graph, fundamentally, but it has one very specific rule.
Which is?
The bars must be drawn in decreasing order of frequency. Tallest bar on the left down to the shortest on the right.
Right. That's the one that helps you spot the vital few, isn't it? Like the 80-20 rule in action.
You got it. It immediately draws your eye to the biggest categories. It basically screams, focus here. Forget the small stuff for now.
Makes sense. But what about pie charts? You mentioned pitfalls earlier.
Yes. Pie charts. They seem so simple, a circle cut into slices. But interestingly, the U.S. Bureau of Labor Statistics actually puts out warnings about poor or misleading pie charts.
Really? Why? They seem intuitive. Slice represents a part of the whole.
They seem intuitive, but our brains are actually quite bad at comparing the areas of different wedges accurately.
Oh, right. We're better at comparing heights, like in a bar chart.
Much better. With a pie chart, especially if slices are similarly sized or if there are many small slices, it's really hard to judge proportions accurately just by looking. The absolute rule is the area of each sector must be perfectly proportional to its frequency or relative frequency. Get that wrong, and the whole thing is misleading.
Okay, so potential perception issues with pie charts. That's good to know. We can see that relative frequency idea clearly in that 2017 U.S. Census data on education. If you look at the proportion, the relative frequency of people whose highest level was high school, it was about, 27%?
Yeah.
0.2713. But then you compare that to those with a graduate professional degree, that was only around 12.3%, 0.1229.
Exactly. That proportion, that 2-to-1 difference almost, it tells a much quicker story about the population's education levels than just seeing raw numbers in the millions.
Okay,
so that's looking at one category at a time. But data rarely lives in a vacuum, right? The really interesting stuff often comes out when you look at how different data points interact, like crossing two qualitative variables. That often uncovers some pretty profound connections. It raises questions like, was there a link between, say, class of travel and survival?
yes. The Titanic example from the source material, a very sobering one. The data set showed, 1,207 people in total for that specific analysis. And the overall numbers were 442 survived, 765 died.
Right. Just raw totals.
But when you break it down by travel class, that's where the story gets stark. First class, nearly 200 survived, about 122 died. Much better odds. Compare that to third class. Only 151 survived, but 476 died. A huge difference.
It's staggering, isn't it? Just by cross-tabulating two simple categories, travel class and survival outcome, the relationship jumps out. It shows data isn't just abstract numbers. It reflects real, sometimes harsh, social realities. That dependency, where one category heavily influences the chances of the other, it's revealed with just a careful frequency count.
Okay, so that covers categories, the qualitative stuff.
Yeah.
What about when the data is actually numbers, numerical values? Now we're shifting gears into quantitative data.
Right. And with quantitative data, the first big split we need to understand is how the numbers behave. Are they things we count or things we measure? This distinction is pretty critical for how we visualize it later.
Okay, so countable numbers.
Yeah.
It's discrete, right? Like how many employees a company has, or pages in a book.
Exactly. Or the example used in the source. How many siblings do you have? 0, 1, 2, 3. Distinct integer values. You can't have 1.5 siblings.
All right. Countable chunks. And the other type is continuous data. That's the stuff we measure.
Yes. Things that can theoretically take on any value within a given range. Think about distance, age, speed, temperature. You don't just jump from being 25 years old to 26. You pass through all the infinite moments in between.
Or like temperature, it doesn't skip from 50 degrees to 51. It passes through 50.1, 50.001, and so on.
Precisely. It flows continuously along a scale. Now, when we organize discrete data, like the number of siblings, we can often treat it similarly to qualitative data at first. We can list the distinct values, 0 siblings, 1 sibling, 2 siblings, and then count the frequency for each. It fits neatly into that frequency table structure we talked about earlier because the values are separate and countable. But when it comes to visualizing quantitative data, especially the continuous kind, or discrete data with many, many values, the simple bar chart isn't really the right tool anymore. We need the histogram.
Okay, histograms. They're like the workhorse for numerical data visualization. But they can look a bit like bar charts to the casual eye. What's the fundamental difference we need to get?
It's a really key difference. A bar chart compares distinct categories. The labels on the bottom axis are names or groups. A histogram, on the other hand, deals with numbers. It groups numerical data into ranges, into intervals. We call these classes or bins.
Ah, so instead of apples and oranges, the bottom axis might show 0 to 10, 11 to 20, 21 to 30.
Exactly. The rectangles are drawn over these numerical classes. The height still shows the frequency, how many data points fall into that specific number range. And crucially, in a histogram, the bars usually touch each other.
Why do they touch? Is that significant?
It is. It signifies that the underlying variable is continuous or treated as continuous. The data flows from one class interval directly into the next without gaps, unlike distinct categories.
Okay, that makes sense. So grouping numbers into classes, that feels like where some decisions have to be made by the person making the chart. Like with that state population data example, what percent of each state's population wasn't born in the U.S.? The percentages were all over the place, right? From West Virginia way down to 1.6%, up to California at 26.7%. Just a list would be messy.
Totally messy. A histogram lets you group those percentages. Maybe 0% to 5%, 5.1% to 10%, 10.1% to 15%, and so on. It brings order to that chaos.
But choosing those groups, those classes, how wide should they be? Does that matter?
You've hit on probably the most critical and potentially tricky aspect of histograms. The class width, the width of those intervals, those bins. First rule, it must be consistent. All classes should span the same numerical range, like 5 points wide or 10 points wide.
Okay, consistency, like with bar chart widths.
Yes, but here's the big warning. The choice of that width dramatically affects how the histogram looks, how the distribution appears.
Wait, so changing the class width can change the story the graph tells, even with the exact same data?
Absolutely. It's a major point of subjectivity and, frankly, potential manipulation.
How so? Give me an example.
Okay, imagine you choose a very small class width, lots of narrow bars. This shows a lot of detail, maybe lots of little peaks and valleys, but it can look really noisy, really jumpy. It might make the data seem more volatile or erratic than it really is, kind of obscuring the main overall pattern.
Right. Too much jagged detail.
Then imagine you choose a very wide class width, fewer, wider bars. This smooths things out considerably. The histogram might look cleaner, simpler, showing a broad trend, but it might completely hide important details, like smaller secondary peaks or dips that could be significant.
So you could smooth over important nuances, or you could make noise look like a signal. That choice of class width seems really powerful.
It is. It's probably the number one thing to be aware of when you're looking at a histogram someone else made. You have to ask why this class width.
Okay, so let's assume we've picked a reasonable class width, built our histogram responsibly. Now, we're not just looking at counts in bins. We're looking at the overall shape, right? The pattern of the whole distribution. What are the main shapes or visual patterns we should be training our eyes to see in a histogram?
Yeah, the overall shape tells you a lot about the nature of the data almost instantly. There are roughly 4 main shapes we typically identify.
4 main shapes. Okay, what are they?
First, you might see a uniform distribution. This is where all the classes have roughly the same frequency. The histogram looks kind of flat, like a rectangle or a plateau. No obvious peaks.
Okay, flat, uniform. What's next?
Then there's the classic bell-shaped distribution, also called normal or symmetric. It has a clear peak in the middle, and it tapers off pretty evenly on both sides. Lots of things in nature kind of follow this shape.
The bell curve. Got it. Symmetrical.
Exactly. Then we have the skewed shapes. These are asymmetrical. You can have a skewed right distribution. This means the peak is on the left side towards the lower values, and the right side has a long tail stretching out towards the higher values.
Skewed right. Tail to the right. What kind of data looks like that?
Think about something like income. Most people have incomes bunched up at the lower to middle end, but then you have a long tail stretching out to the right, representing the few people with very, very high incomes.
Ah, okay, that makes sense. So the tail tells you the direction of the skew.
Precisely. And the opposite is skewed left. Here, the peak is on the right side, towards the higher values, and the long tail stretches out to the left, towards the lower values.
Tail to the left. What's an example there? Maybe scores on a really easy test. Most people get high scores bunched on the right, but a few low scores tail off to the left.
That's a perfect example. Scores on an easy exam often look skewed left.
Okay, uniform, bell-shaped, skewed right, skewed left. Those shapes give you a quick read on the data's character.
They really do. Now, one last thing on visualization. Histograms are great for one quantitative variable. But what if you want to see if there's a relationship between 2 quantitative variables? Like, does height relate to weight? Or does study time relate to test score?
Right, looking for connections between 2 different sets of numbers measured on the same people or things. What do we use then?
For that, we need a completely different tool, the scatter plot. That's the go-to visual for exploring relationships between 2 quantitative variables. It plots individual data points based on their values for both variables. #outro.
Okay, wow. We've covered a lot of ground here, from just, counting things in categories, qualitative data, and seeing how even simple bar charts need careful construction, making sure those bars have equal width, for instance, to avoid accidentally misleading people.
Right. And then we moved into the world of numbers, quantitative data. Discrete counts versus continuous measurements. And we saw how the main tool there, the histogram, is incredibly useful, but it comes with that really significant decision about class width. How you choose to group the numbers fundamentally shapes the visual story you tell. The method really dictates the speed and, crucially, the integrity of the insight you get.
So, thinking about that class width thing, it leaves us, and you listening, with a final thought to chew on. If just changing the width of the bins in a histogram can make peaks look sharper or smooth them out entirely, how often might we be looking at charts, maybe in presentations or reports, where that specific class width wasn't chosen to reveal the clearest truth, but maybe, just maybe, to subtly obscure something, or perhaps exaggerate a pattern the presenter wanted us to see?
It's definitely something to keep in mind. Always question the setup of the visual.
Be skeptical, be curious. Thanks for joining us on this deep dive.